x square plus y square. So I'm saying see this as f of x1 actually. Okay. So now this is the function of x. One is like fixed. Okay. One is like fixed.
Wouldn't it change the different values of x because it is in one?
Because
So c minus.
so this would be x square plus 1. Obviously, when you're going to x expression, go to g then. But I'm not interested in the expression, I'm interested in knowing that, what would be the output of this condition. So if you treat this and see this as an expression depending on x of s with this constant part in it, so just treat this as that, not doing anything with this part. This is like a constant part of that. Actually, you probably can get up like look at from the perspective of that. That's that order of it. Many other properties, for example, much can be said about Brownians. You can write an entire book on just properties of the Brownians. But we try to hit the key properties. For example, if I say you make a list of the properties that we have proved, then what should be that list about Brownians? By the way, I must say, in our discrete time part, we defined stopping times, okay, and then we did algebra of stopping times, we added them, making minimum, maximum, all this is stopping time defined. For example, stop process, then stop simple fields, and then we said that stop processes are adopted measurable with respect to the stop signal fields, and we prove that process is a martingale, the stop process goes to martingale, and then finally we prove something what we call the optional sampling theorem, which simply says that if you take for example martingale and compute its conditional expectation at a random time tau, okay, given everything about the process up to the for example that time tau or another time. Okay, so this was imagine this. So if you have a mu and tau actually, so there are two random times in a day. Okay. Then proved that if I have a martingale, look at this process at instant tau given, I know everything about process up to the mu. This must be same as m of the w.r.t. So it's like a very much generalization of the stop process. Okay. This was optional sampling theorem. Yeah. So in other words, imagine. So I have it today, and this is like 10 p.m. 10 a.m. Okay. So what was kind of a random thing. So you pick the walk and you say, let's check the the status of the stocks today. The status is not good for you. Okay. And it's a random time. Then you select another random time in the evening. So we're going to say, okay, how much would my portfolio worth at a random time in the evening? So we're going to say, so optional sampling theorem is telling you that if you are interested in computing the worth of your portfolio, for example, your stock or whatever you own, at a random time in the evening, okay, so the value should be same as whatever the worth of the portfolio today or at the moment is. So it's like a generalization of market process. Martingale problem. Now the point is, all of these results or also true in continuous time. So I'm not proving them. Okay. You have, so you can take a continuous time process. You can define, for example, the stopping time. You can define. So just go through this section. Actually, it's not saying prove it everything. What if you go through that things? But all these results are also true in continuous time. So like optional sampling theorem. So if you have a continuous time process, that is a martingale, and if you stop that process, okay, at a stopping time. In other words, you take the minimum of a stopping time, and previously we were taking what? So, remember? So you are taking tau, minimum of tau or n. Okay. So, in other words, so what does this mean? So I'm going to stop this process at tau. So if it didn't stop, I'm going to stop it at n anyway. So this is like you have this process. Either is going to stop at a time tau. And then, if it doesn't stop, this event doesn't occur, then I'm gonna stop anyway at n. So in other words, instead of n, now you can replace p. And the result is still holds. Okay, the stop process is adopted, the stop process is martingale, and the line process is martingale. You also have optional sampling theorem and so on. So, yes. So can we list what are the key properties that we did about, for example, Brownian motion, define Brownian motion. Okay, then we talk about when a Gaussian process is Brownian motion. Okay. Then we said that Brownian motion is nowhere differentiable. In other words, if you take a trajectory of it and you want to differentiate it at any instant over the time, you can't find an instant where you can differentiate it. It's nowhere differentiable. Okay. And then we also proved that a more generic result which says that if you take an instant and look at all possible trajectories, okay, they will not also be differentiable. Okay. So we also proved it. We proved that the Brownian motion has independent increments. There are different examples of Brownian motion. Okay, it has the Markov property, has continuous part, that's part of the definition. So we did some of the properties, and you should always have these properties. This is an important thing that you should always keep these properties in mind. Okay. One thing that I would like to do, that probably not in the class, but maybe we'll do a seminar or something like that. Why does the Brownian motion exist? What are the proof that it exists? So you have defined a bunch. You have defined, so it's a class of processors. Okay? And so you define the Brownian motion through certain blocks. But the question is, does this process exist? Prove the existence as well. And I think we should push more and do the more condenser rather than just fixing over it and get to a seminar or something like that. So it's a pretty easiest proof. One thing that I haven't proved yet is also that Brownian motion is also Holder continuous actually. So Holder continuity is like, so we know that every differentiable thing is continuous and continuous and not differentiable. But Holder continuity is something in between actually. Continuity and differentiability. So Holder continuous functions are continuous. Okay. But not that differentiable actually. So Brownian motion is also Holder. I can just suppose it just need to satisfy, for example, it just need to satisfy very formally speaking, just need to satisfy that the increments of the Brownian motion. If you have an increment of Brownian motion, it satisfies an inequality. S is less than or equal to some constant times of E minus S. If this would be the case, what do we call, for example, Brownian motion? So this would be like the uniform quantity, but it's not uniform. Yes. There is going to be some exponent here, gamma. The gamma need to satisfy some property that also has these modal continuous trajectories. Just post the proof of it and read it for yourself. These are the basic properties that we should keep always in our elementary. Much can be said about Brownian, right? You can write entire books on. So there are entire books on this topic of the Brownian. Just listing the different properties of each. I'll just give you a heuristic picture. Let's move to a new topic. That is going to be how to integrate with respect to the Brownian motion. How to integrate with respect to the Brownian motion. Itself a big topic. Glimpse of it. Obviously, we can we define the integral of some function, some suitable function, for example, with respect to the Brownian motion. In Riemann-Stieltje sense, actually. We discussed it last time that we can't. Why? Because it doesn't have finite evolution. We can't. So we have to create a new, entirely new, what do we call definition. So yes, we have to create an entirely new definition of species. I would like to begin with, for example, L2AB. So this is like the collection of all the square integrable deterministic functions. You can take AB to be, double 0t. As a space of all square integrable functions. We know have a complicated structure, it's a infinite space, we know everything. I'm going to assume that I know that this set of step function is dense in it. So this is also a kind of a fact that if you take the step functions, it's also dense. So I would like to define what is the meaning of integrating a deterministic function that is a square integrable, say with respect to that Brownian motion. So that will give meaning to this species. I would like to start from here. What is the meaning of integrating a step function over, say, over an interval, b with respect to the Brownian motion. So let's start. By the way, such an integral, so if you are integrating a square integrable function with respect to, say, Brownian motion, such an integral is called a Wiener integral. Okay? So it's a Wiener integral that I am interested in defining. Okay. So let me take an f. So let me take an f from here. So imagine f is a step function. So if it is step function, I can abstractly write it as the linear combination of some constant that it takes, okay, multiply the indicator functions. So what does this mean? That f of t is a1 when t is in the interval a1, okay? Okay. So I know that indeed this belongs to a. Okay. So So there'll be more questions. You'll be more questions. It's not a quickly jump over things. So let's take the interval A to B and let me partition it. This is like T0, T1, T2, and Tn. I know my f is, somehow defined over this interval. You can have some value, not necessarily continuous, but it's square and parallel. Okay.
So L2 से ले
L2 the step function would look like that, okay, in this interval it takes this value, in this interval it takes this value, next interval it takes this value, takes this value, and so on.
हाँ
Okay. This is like my A1 and A2 and maybe A3 and A and so on. Okay. I'm going to say f of t is the sum of I equal to 1 to n, ai and the indicator function of pi to say pi minus 1 to 2. So how should I define it? So I would like to integrate this f over the interval. So what do you think? What should be the value? What should be the value? In other words, so if I be more precise, what I'm trying to do, I'm trying to define an I, okay, that takes inputs from L to K, okay, and throws it into L to omega. Okay. So L to omega is the space of square integrable random variables. We don't have deterministic things, but so it's a space of. So what is the norm here?
So L2 norm
So it's a 2 norm, and what are the norm here? So we define true expectations.
expectation
Okay. So I would like to first define this I over such a step function. The question is, what should be, and I'm defining say I of f, A to B, f of E. And you can basically say, how do you know that this integral is that? I would like to define I of f as an integral of this step function f. So the question is, how should I define it?
should we take help from increments of the
Yes. So what we can do is that take these values and multiply with the increment. Really the Riemannian motivation. So I'm defining I of f to be something. And keep in view that at the moment f is not from L to AB, but f is from some part of L.
then it is dense then it's
Currently I'm only defining f for step function. 1 to n, ai and w of pi and w of pi plus 1. Okay, so what is the first? What is the first question you can ask? Is this well defined? Is it well defined? The only thing that we need to verify is that if this species goes here actually. Yes, you just take that, just square it and take the expectation. So it's finite actually, so it's there. Okay. And then I can see that this I, when it is defined on the step functions, okay, step functions, should write a step actually, so that you should infuse this f with an abstract f. Okay, that it has all basic properties. I of f plus af A plus BG, where F and G are two step functions, same as R of F plus kind of so everything is simple. G. Now I'd like to take an abstract function from a theorem. So I know that this guy is what? Is dense in L2. So I can find a sequence of step functions that approximates f in L2 sense. Okay? As I move to okay? So what do you think? What should be the integral of this? Or what should be the I for I of f for f? So what we can say is that, just compute, for example, the I of fn and see that whether it converges or not. If it converges, and it will converge, then just give that limit a name. And what name that should be? So I would like to talk about I of fn. I'm finishing. So I would like to argue it converges. It converges. It converges. So how can I show it converges? Many strategies. I know that fn converges to f. So how can I show that it converges? So only thing that we need is the convergence of this sequence of step function. So just show it it's Cauchy. Just show it it's Cauchy. So how can I show this is Cauchy?
Sir, I have a difference larger.
So we need the of fn minus I of fn. Okay.
L2 sensitivity.
Okay. And this would be same as, if I write it explicitly. Okay. So this would be same as, say what? Sum, say I equal to 0 to n. Fn is basically given by ai's. This is defined through some bi's and indicate the function of ei minus 1 to
Yeah.
this would be fn minus fn, not the I of fn. So I of fn minus fn would be what? I equal to 0 to n and ai minus bi times increment. Okay. Of w of ei plus 1 minus w of ei minus w of ei minus 1. ei minus ठीक है जी? Is it making sense? So what would be the, so I need to do what? Square it, because this is a species here, square it and integrate. So I fn minus fn square would be what? So it's going to be I equal to 1 to n and ai minus bi square times the expectation of the square of the increment, which is pi and pi plus already else. Okay. Can you make sense of this example? What is it? Okay, this is nothing. It's the square of the integral from a to b of fn minus fn square and PG. Okay. But I know Fn converges to Fn and L2 every cells. Okay. As n goes to infinity. Okay. As n goes to infinity, this must go. So this shows that this partial sequence converges. Since this converges, it has a limit. It's a complete Hilbert space. It's going to have a limit for sure. And whatever that limit is basically this. In other words, what I'm saying is that this is the limit of n goes to infinity of the integral of I of Fn's, but these are Fn's are those Fn's which are approximately.
Sir, L2 to layer special reason L2 to layer
इसमें
is पूरी मतलब analysis
two things in Hilbert space is very real.